Okay, so we have everything that we now need to write our integrals in terms of coordinates in the parent subdomain. So let's just go ahead and write that. And in particular, the integral that we are working with is the following, right? So actually, let me title this integrals in the finite dimensional weak form. And in particular, we are working with this integral. All right, and where we are is a realization that this integral can now be written as minus, right? And that minus comes from the constitutive relation. We've agreed to pull the sum out and write it as a sum over a and b, and for brevity, we're not writing the limits that a and b run over, right? In the general case, they run over 1 to number of nodes in the element, each of them, all right? We have an integral now, okay? And inside this integral, we have terms of the form, out here we have C, A, E, right? We don't want to forget that. Okay. The integrand is made up of terms of the following form. Na, comma, I, C, capital I, comma, little I, kappa, ij, NB, comma, capital J, C, capital J, comma, little j. And now, previously we had dV being the elemental volume in the physical subdomain. And we've just agreed at the end of the last segment to write it as in terms of an elemental volume in the parent subdomain. But that does involve our including the determinant of J here. And let's recall that it depends upon C. Okay, d, v, c. The integral here now can properly be written as an integral over omega c. We recall that this is the integral which we enclose in parentheses, and we have here d, b, e. Okay? All right. Now, if we stare at this integrand, it looks a little daunting, doubtless, but we observe that there is a the Einstein summation convention is at work, and so really what we have left is going to be an expression which takes on values depending upon the specific element degrees of freedom, capital A and capital B. Okay, the capital I, capital J, little are going to be, so to speak, contracted out, right, to use the terminology of tensors and vectors. Okay, right. So when we carry out this integral, and let's assume that we do know how to carry it out. First of all, observe that this integral can be is easy to carry, is relatively easy to carry out because our domain omega c is a nice regular subdomain, right? So it's a nice regular domain. It's a bi-unit domain. So let me just write that little bit here. Sorry, integral over omega c is the one thing that I wanted to make a difference with the way I wrote. So this is now a triple integral, okay, where c 1 equals minus 1 to 1, c2 equals minus 1 to 1, and c3 also equals minus 1 to 1. Okay, everything that we have in here, I'm not going to explicitly write them as depending upon Xi, but we do recognize that indeed Na comma I will depend upon Xi because Na is trilinear, right, in the X's. Okay, so derivative with respect to any one of those coordinates is going to leave us with something that's bilinear. In general, it will depend upon two of those X's, right? If you look at Xi I comma I, and you recall how we're going to compute it, it too will depend upon Xi. And why is that? Right, that's because we are going to compute it, we're going to identify it as being the components of the inverse of the tangent map, right? And the tangent map consists of first derivatives, right? So this too will be a function of Xi, right? Kappa ij, well, it depends. If we have something with uniform conductivity or uniform diffusivity, it would be a constant, right? But that does not, we are not restricted to that. We could have something that's a function of, this thing could potentially be a function of position, right? Could be a function of position, and because we know how to write the physical position as a function of Xi, that too will be a function of Xi, all right, the kappa. Okay, and then we have NB, which of course we've already discussed, right? We know how to write its derivatives. It's going to depend upon Xi, as will the derivative of Xi itself with respect to little x, little j, right? And then again we have the determinant here. Okay, and this again is an integral over Xi1, Xi2, Xi3. We close our parentheses, right, and all of this is multiplying dB element E. Okay, so everything in that integrand is properly a function of the Xi1, Xi2, Xi3. That integral can be carried out. All right. For simple cases, actually, this integral is not that difficult to carry out analytically. And by simple cases, I mean things, situations where kappa is indeed independent of position. Okay. However, we are not going to get involved right now with evaluating it analytically because we already have a way to evaluate this. Right? Do you remember how we're going to evaluate in the general case? Right, using numerical integration. Okay. So we'll come back to that later. We'll come back essentially to how to do that in 3 dimensions. Okay, but the point I want to make now is that if one looks at the integral here, okay, that can be evaluated. It's going to give us a scalar value, right? Because all the little i's, capital I's, the little j's and capital J's are going to be contracted away. It's going to give us a scalar value, however, that is going to be indexed by the capital A and capital B corresponding to the local degrees of freedom. Okay? So I am going to denote this K AB sub E. Okay, the AB is obvious why it needs to be indexed by AB. It's also obvious why it needs to be indexed by little e. Okay, because this is for a specific element. Okay, and so we have it. Our integral on the left is now just minus sum over A comma B C A E K A B for element E D B E. All right. And now we take a step that we took in the 1D case as well. We are going to, well, actually, what are we going to do? Do you recall what we do next in setting up our finite element equations? We get rid of our sum, our explicit sum over A and B by going to matrix vector notation. Okay, let's do that in the next slide. So what we're doing is using matrix vector notation for local degrees of freedom. In order to keep track of local degrees of freedom, we're going to use matrix vector notation, right? And really for their numbering. Okay? And what this means is that for element E, if we have C1E, C2E, up to C number of nodes in the element E, right? These are the degrees of freedom, as you recall, that are used to interpolate the weighting function using our basis functions, right? Okay, so using this, right, and of course the same thing for D's, D1E, D2E, all the way up to D number of nodes in the element E, right? Using this, what we observe is that we essentially are able to write our integral, right? This implies that we can write integral over omega E as, now, minus, we're going to write the C vector as a row vector, right? And you recall how we did this in the 1D case as well. Okay, we get a big matrix here, which consists of entries K11E all the way up to K1 number of nodes in the element E. Okay, and the last entry here is K number of nodes in the element times number of nodes in the element E. Okay, that is the matrix that we get, and this is multiplied by a column vector using the notation that is sometimes employed in linear algebra. Okay, right? And for even further brevity, we could write this as minus CE, right? Where CE or CE transpose is that row vector, right? This KE, right? KE is the matrix, DE. Okay? And by reference to what was done in the 1D case, we would call this the element conductivity or diffusivity matrix, right? Depending upon what problem we were solving. Depending upon what physical problem we were solving. Okay? All right, clear enough, hopefully. We can now follow exactly that same approach to look at the first integral on the right-hand side of our finite dimensional weak form. Okay, so now consider integral over omega E WH F dV. with everything we've gathered together, this should be relatively quick, right? We are going to write this as integral over omega e. The WH, you recall, we will write as a sum over a, NA, okay, no derivatives here, right? So we have NaCAE. I'll put parentheses on this to remind us that this represents WH, multiplying F dV. Okay, we can take several steps all at once now. Let's do that. Let's pull the summation out. CAE. We have an integral over omega e, but let's plan to write that with a change of variables as an integral over omega c. All right. Inside here, we continue to have NA because it does depend upon position, multiplying F, and let's recall that F could be a function of position, but through our mapping, we have that. Okay, and NA, of course, is a function of position. Okay, we're writing everything as a function of coordinates in the parent subdomain. That leaves us with just dV, right? But we know how to handle that. We know that it's just determinant of the Jacobian of our mapping, dVc. Okay? Sorry, that's a little too squeezed in there. So let me write it out here more clearly. Okay? That's what we have, right? And of course, this is, now again, we can take several steps at once. So we can write this now as we can abandon our explicit writing of the sum over A, right? And we know how to do that. That can be done by going to this row vector notation for the C degrees of freedom. The integral now explicitly is a triple integral. C1 equals -1 to 1. C2 equals -1 to 1. And C3 equals -1 to 1, right? Our integrand here consists of a column vector of the of the basis functions. They're often called shape functions, but it's a term that I've been avoiding. Okay, we have the basis functions. Right, we have this. We have f, right, which could be a function, which could depend upon c through x. We know how that dependence comes about. There is an abuse of notation in using the same symbol f, but I will just adopt that abuse of notation, right? And then we have determinant of j, function of that position. Okay, we have this, and yes, and we observe that this integrand is essentially an this integral is over dxc1, dxc2, dxc3. All right. Okay, we can compute this integral in general. Again, we will look at how we handle these types of integrals using numerical quadrature, numerical integration. And we observe that we essentially get what I will write out as being C1e, C2e, C number of nodes in the element E times a column vector which I will denote as F internal, okay, degree of freedom 1 in element E, F internal, degree of freedom 2, element E, coming down as far as F internal degree of freedom in E element E. Okay, and finally we could write that as C E transpose F internal for element E. Okay, all very nice and concise, right? And the advantage is that having done it with in excruciating detail for the 1D case, we know immediately how this needs to work out. All right, we'll stop this segment here.